Welcome everyone to Guided Study Group of Math 140, week 13. This week we're going to be working over section 4.3 to 4.5, which is basically the fundamental theorem of calculus that shows the relationship between differentiation and integration. Then we have indefinite integrals and the net change theorem. And finally, we have the substitution rule, which is kind of like one of the techniques that help you find integrations of a little bit more complicated functions. This is also kind of like the starting point of what you guys are going to be learning in 141. At least for the first midterm, it is going to be all integrations. So this is a very good start to kind of like master it before you guys get to the next level. So having said that, let's get started. So first off, we have 4.3 fundamental theorem of calculus. So the fundamental theorem of calculus says that suppose you have f is continuous from a to b, then you're gonna have gx is going to be the integral from a to x of ft dt. So your function f have to be continuous for this gx to exist. Then you have your conclusion is that g prime of x, so derivative of g is going to be f. And g is going to be continuous on this interval as well, and also differentiable on this interval. Of course, it's differentiable because when you differentiate g, you're going to have fx, and so it's continuous. Then you kind of like have this fundamental theorem of calculus 2. So the integral from a to b of fx dx is going to be big F of b minus big F of a, with f be kind of like the most general antiderivative. F is an antiderivative of f. That is a function f, big F, such that big F prime is going to be f. Some problem that you might be asked in this sections is that you'll be given gx, or this function derivative from a to ux of ft dt. They're gonna ask you to find g prime of x, or like this is just another way to write it. Then or you can be asked to evaluate the integral from a to b of fx dx or related work problems. So having said that, let's get started with the example. So the first example is going to be question 14 of section 4.3. So find the derivative of hx from 1 to square. It's the integral from 1 to square root of x of z squared over z fourth plus 1 dx. So this one is kind of like we have to use the chain rule a little bit. So you have integral of this thing, z squared over z fourth plus 1 dz. If you put square root of x as u, you're gonna have d over du 1 to u z squared over z fourth plus 1 dz multiply du over dx. So this part is going to be u squared over u fourth plus 1 multiply. So du over dx is just square root of x prime. And so for this one, we're going to have 1 over 2 square root of x. Now, if we find our final answer, must be in the form of x. So you're going to put everything back into x again. So you have x squared plus 1 over 2 square root of x. So simplify that, we have 2 x squared plus 1. So the important part is being able to write this one down, because here you have kind of like instead of x as one of the boundary, you have square root of x. So you have to use the chain rule to make sure that you account for the fact that this is square root of x and not x. This is what we're doing here. And in the du over dx. So when you do the change of u instead of square root of x, basically you just simplify the expression a little bit. So that is example 1. Example 3, evaluate this integral. So this integral we have from 0 to 4 minus t square root t dt. So you have give me a second. So first we find 4 minus, what is the antiderivative of this? This one is going to be 4 square root of t minus t square root of t dt. Or you can rewrite it in the way of 4 t to the half minus t to the 3 half dt. And this one we've learned last week of how to find this antiderivative. So when you say f is just any antiderivative, you don't need to care about, like, you just need to find one antiderivative of that. You don't need to find all of the antiderivative. And so for here, you're just gonna have 4 minus over 2/3, 4 multiplied 2/3, because it's 1 over 3 half, t over 3 half minus 2 over 5, t to the 5 over 2. So this one is coming from the fact that integral of x to the n dx is going to be x to the n plus 1 over n plus 1. So if we simplify that, we have t to the 3 half to 5 t to the 5 half. So you're just gonna plug it back here. So you have a third t to the 3 half minus 2/5 t to the 5 half. From 0 to 4. So when you plug in 4, what you have is a third, 2 to the third minus 2/5, 2 to the 5th. And then 0, when you plug in 0, 0 is just going to be 0. So what you end up having in this question is that you have 2 to the 6 over 3 minus 2 to the 6 over 5. So let's get down here. This one is going to equal 2 to the 6. 3 minus 1 over 5, which is going to give me 2 over 15. So it's 2 over 2 to 7 over 15, which is, I have 128 over 15. So the important part here is the first step, find the antiderivative. Then you start plugging in the boundaries of these two, and that's the fundamental theorem of calculus 2. So that is example 2. Now example 3 is question 57. So this is, they give you fxb, this one expression. Find equation of a tangent line to the curve f y equal f prime of x at the point x equal pi. Now this is where you have, so again, the general equation of tangent line is y equal f, I would say f prime of x0 is going to be pi x minus pi plus f of pi. So we have, first is f of pi, you want to plug in, it's going to be pi to pi. So the integral from 1 point to 1 point, which is going to be just 0, because it's going to be the integral function, and then you have, say, if you have that one is g of pi minus g of pi, essentially, with g is the antiderivative of this function, then you're going to have this one is just 0. Then now you have to find f prime of x. So this one is d over dx pi to x cosine t over t dt. And this one, by fundamental theorem of calculus, the first one, you're going to have this one is cosine x over x. Therefore, you're going to have f prime of pi b cosine of pi is -1 over pi. So your tangent line now is just plugging in y equal -1 over pi x minus pi plus 0 is just nothing, so it's negative 1 over pi x plus 1. So this is my answer for the tangent line equation. So the most important part is being able to realize this 2 point. Two key part is that the integral from pi to pi of a function is 0, because it's definitely just that function minus itself. And then finding the derivative of the given function is using the fundamental theorem of calculus to figure that one out, and you just plug in pi to find the slope of the tangent, which is here. And then finally, you just put everything together into the function of the tangent line. Now, let's go to section 4.4 and 4.5. So 4.4 is where you have indefinite integrals. And so the definition of indefinite integrals is a function, big Fx, so that you have f prime of x equal fx always. Now, there's a very big distinction between indefinite and definite integral is that indefinite integral is notated as just s and fx. You don't have any boundary, and you end up your final result regardless of what you do in between. It's always a function. But if you put the boundary in from a to b of fx, definitely that will be a number, because eventually you're gonna have two values minus one another. So this is definitely gonna be a number. So that is a very big distinction between these two. Then you have the table of indefinite integrals. This is kind of like just a summary of common functions that you guys gonna see, and just like applied it and use it. And I think you guys really familiar with it. The only thing that might be a little bit different is this plus c, because you're looking for the indefinite integral. In other words, the most general antiderivative, you need a plus c, because when you take integral, this one is going to definitely give you fx, but this c is always 0, right? You don't know what constant if you add a constant to your function, you still get whatever function that you're having here. So the most general case is plus c, with c can be any constant. So then we have 4.5. One way of finding integral is using substitution rule. So when you're gonna have, say, instead of just a simple fx dx, and it's gonna say you have a function that doesn't really fall into one of your one of the expression you have in the previous table, then you can make a substitution with u equal gx. So say if you have something related to square root of x here, you can do the substitution of u equals square root of x to make everything simpler. And so u equal gx is going to be a differential function whose range is in an interval I. And you have f is continuous on I. Remember, this is important, because without this part, your function wouldn't really be able to count at all. So you have, then you can rewrite the expression of whatever you were given, fx dx, as f of gx multiplied g prime of x dx. And so this, because you have to rewrite the expression, this is the result of a lot of practice and trial and error. So do not expect that, I wouldn't expect that you guys can choose the right function at the beginning, but I will be able to see that you guys getting quite close to it. The solution might be a little bit longer than expected, but it should be, doing a lot of practice should get you guys to the point that we need. And so you basically rewrite expression in every term of u. And so just follow what we did so far, with u be the variable instead of x. So you find that, choose u equal gx, so du is going to be something of dx. Then you put all the integral in u only, take integral with respect to u, and return to the form of x. Now, if you were given a definite integral, so with boundaries from a to b, when you do the change of variable from x to u, so from x to u, you have to do the table of change of variable. So basically, you have a to b, you're going to have ga, gb. So your new function here, you're gonna have new boundaries. And just to make sure that this function over here, when you rewrite it, will have nothing more to do with x. So that's up to your choice of rewriting the expression and also your ability to do some algebraic manipulations. So g prime have to be continuous and f is continuous on this range as well. So you have integral of symmetric functions. So this is kind of like a supplementary part, but I think it's really helpful because if you were able to see, like, if a function f is inside of the integral is even or odd, and you can use one of its kind of like property is that if you have an even function, the integral on a symmetric interval is going to be 2 times of the integral. Say from initially you have negative a to a, then the next one is going to be from 0 to a fx dx. Or on the other hand, if you have an off function, that integral on a symmetric interval is going to be 0. Just like it will remind you guys of this pictures when you have this happening. So that is all the theory that we have, and I think you guys have been really familiar with these through the lectures. So now we're just going to jump into the example. Now example 4 is question 15 of section 4.4. Find the general indefinite integral. So here what you end up having should be a function of this part. Now you have 1 minus sine cube t over sine square t dt. Now I would say this one doesn't really fall into any fundamental expression in that table, but there's one thing you can do always when I see a rational function and I can separate them, is that I can do 1 over sine square t, because here you have, I mean, if you just keep it that way, you wouldn't be able to do anything with it. So you should think about some algebraic manipulations that you guys have to make to kind of like come out of the answer. So when you do this separation, which is essentially the same what we have earlier, I'm just separating it into 2 fractions. Then what you have is here you have cosecant square t minus sine t dt. So here now you can have 2 expressions that actually works. So basically this one is just equal cosecant square t dt minus sine t dt. This one is going to equal, or you can rewrite it as negative sine t, because the integral of cosecant t is negative cotangent t, and the integral of negative sine t is cosine t. Remember, this is cotangent and this is cosecant. And then you add the plus c so that you have the most general indefinite integral. So basically, I think the step is very similar to what we did last week. It's just the fact that now you have to remember the SC in it, because now you're looking for the most general indefinite integral. And also the I think the antiderivative here is going to be a little bit more challenging than last week, because now you should be able to do the algebraic manipulations, and also we start to use a technique of U substitution, which is going to be our next example. So our next example is question 21 of section 4.5. Evaluate the indefinite integral in this form. Now, one of the things that I just showed you guys is if you have a function in the form of square root of x, the first thing you should think about is take u equals square root of x. Or if you have square root of x plus 1, you're going to take u equals square root of x plus 1 most of the time, not always. But here it's kind of like the same way. So my first guess is that I actually will do it 2 ways. I'll first use u as square root of 3ax plus bx cubed. Therefore, I'm going to have du equal half of 3ax plus bx cubed to the negative half, multiply the derivative of whatever inside the square root. It's going to be 3a plus 3bx squared dx. So you're gonna do some simplification here. 3 over 3a plus bx squared dx over 2 square root of 3ax plus bx cubed. Or this one, if you do some, you basically have the entire function up here. So you can rewrite that's 2/3 dx. du is going to be equal whatever we have in the equation. So if I call this one I, just for the sake of shortening your answer, you're gonna have I equal to this integral and this integral. So you're gonna have, so this integral is going to be integral of 2/3 of du, which is really easy now because it's going to be 2/3 of u plus c, or you can just put it back everything in the form of x, and you must do that because this is the integral in the form of x initially. So that is one solution. Another one, if you guys are not really quick with are not really familiar with this thing yet, there's one other thing you can do. Du is going to be 3a plus bx squared dx. So your I right now is not going to be as simple as this one, but still you can change something. So here you're gonna have du over 3. So I would write one more thing. Du over 3 is going to be a plus bx squared dx. Remember the dx here, do not throw it away, because usually I think in the exam you throw it away. Sometimes it's really difficult for you to track back of what you're doing, because you're gonna be, when in an exam, usually you're gonna be really focused, and when you check back and you find, okay, I don't know where my dx goes, or I couldn't keep track of my u substitution. That's when people start to freak out and start to lose track of what they're doing, because they wouldn't keep up with it. They forgot the dx every single time that they take u substitution. So be really careful with that. And so in the denominator, you're just gonna have square root of u. So you're gonna have basically 1/3. I'll take it outside. Du over square root of u, and now it's just going to be the integral of u to the negative half du. And so 1/3 multiply 1 over 1/2 is going to be 2, because this one is, now you're going to start using x to the n dx is x to the n plus 1 over n plus 1. So n plus 1 here is going to be half, and divided by n plus 1, so it's going to be 1 over 1/2, so it's going to be 2. And then u to the half plus c. Or you're going to have 2/3 square root of u, which is going to be square root of what we have earlier, bx cubed plus c. And so we do it two ways, but it should give us the same answer. Well, it should be. It's just two different ways to do it, and you can clearly see like the length is generally the same, but the final answer of the integral might be a little bit shorter on the left, but it requires the fact that you have to be very sensitive to, or sensible to, these type of questions and be able to do the algebraic manipulations right in your head. But I don't think it really matters as long as you get the answer. It's just slightly longer. It's not like 2 pages longer, so it shouldn't be a problem. But feel free to try it out with taking different u substitution, just to make you guys like more familiar and more comfortable doing this kind of exercise. Now we have example 6. It's question 51. Evaluate the definite integral. So the first thing is always trying to find what is the indefinite integral and then just plug in. So I would say first I would try to find dx over 1 plus square root of x to the 4th. Now you can do u substitution here, because I would honestly say I couldn't really think of any other way to do it. You guys didn't really learn anything about the 4th power expansion of like expansion of a fourth power. So I would say here I would do substitution, and when I first think about it, I would do u equal 1 plus square root of x. There are two ways. You can do u equal 1 plus square root of x, or u equals square root of x. That's fine. I can try. Let me look at the next slide. Yeah, I can try doing the auto substitution in the next questions. That one's going to be slightly longer again, but it doesn't really matter. So do EU is going to be 1 over square root of x dx. Now, you look at the expression, you don't have any square root of x separately. So the way that you're going to do it is here you have 2 square root of x du is dx, right? You only have dx in the numerator. But you have u be this, so you have square root of x is going to be u minus 1, right? That's when you can plug it in here. So again, this is all about manipulation. 2u minus 1 du. So your integral right now is going to become 2u minus 1 du over u fourth. So I'm gonna make it simpler by doing separation, like separate it into two fractions and kind of like divide each of them individually. So you have 2u to the negative 3 minus u to the negative fourth du. So things are easy now when you can take the integration. So I would say there are two ways you can do this. You can take the indefinite integral first and plug it in, or another way I can integrate it in at the same time. But when you go from x to u over here, you need to do the change of variable. And I try to put it in here because I want you guys to kind of like increase the speed a little bit. Since in 141, I would say you're gonna just do 2 steps at once, so you don't separate them out and then plug it in again. I would say try to do it this way. At first, you might not be familiar with this. You might have to separate them, do the indefinite integral first and plug in the number. But as you go through more practice, I would say try to do it this way. Integrate the boundaries in to kind of like shorten your answer a little bit. So you have this u when x equals 0, u is going to be u1. So basically you just plug in this expression. And when x is 1, u is 2. So it's from 1 to 2. 1 to 2. So here when you take integral, here you're going to have 2 multiply. So when you have n equal negative 3, after that you're going to have 1 over negative 2, u to the negative 2, minus 1 over negative 5, or negative 3, u negative 3. So now it's from 1 to 2. So coming down here, you're going to have negative u over to the negative 2 plus 1 over 3u to the negative 3 from 1 to 2. So now you're going to have negative 2, negative plus 1/3 u negative 3 minus. So this one is that one. So you have this minus is when you have in the one FB minus FA. So FA is now you plug in 1. So negative 1, negative 2 plus 1/3, 1 to negative 3. So what you end up having is going to be negative 1/4 plus 1 over 24 plus 1. So here, negative with negative is a plus. And then you have negative 1/3. So what I end up having in this question is 51. I will have the answer be I forgot here you have a 2. You have a 2. Sorry for that. When you do 2 inside, I forgot to distribute it in. So what I end up having right now is that you have 2, 2. See, 2. So this one is 1 over 12 instead of 1 over 24. And this one is 2/3. So end up is, I think I have 1/6. Yeah, should be the case. So final answer 1/6. So first doing substitution, remember this change of boundary. And a trick here is being able to write this down. So when you usually don't see where square root of x in the expression, you can try to look back at your substitution and plug it in. And so now we're going to go to the second way of doing substitution for this. So our integral is from 0 to 1 dx of 1 modulus square root of x to the 4th. So when you do u equals square root of x, you have du be 1 over 2 square root of x dx. Again, you don't have any square root of x separately in this question, so you're going to have, so you have dx be 2u du. Again, change of variable, x and u, 0 and 1. You're going to have 0 and 1 again here when you plug it in. So end up having 0 to 1, 2u du, 1 plus u to the 4th. Now, from here, I will say it's stuck. So you don't know what to do next from here because you wasn't able to do any change of variables anymore. So I would say this is when you come to the fact that you can take wrong, not wrong, but oh shoot, yeah, I think I just missed it, but I'm gonna put it back in, don't worry. So I would say the second way of doing u equals square root of x is not a very nice way, but that's all come to trial and error, so no worries about that one. I would say so for that, that's all I have for today. If you don't have any more questions, I'll stop the meeting here. So do all of the practice problems that you have in Canvas and also the additional question of 4.4, question 49. I think that one is really helpful. So having said that, I'll stop the recording here and I'll see you guys next week. Have a great weekend, guys.